Welcome everyone. With this, we come to the third session of the day. This session is from Pune chapter, Impact of Quantum Computing by Rashmi Tambe. Before we start the session, let me thanks our founding sponsor, Innovation Roots. Innovation Roots is a leading consulting and training service provider, helping organizations to achieve business agility and beyond. It is one of the leaders and pioneers of niche publishing services and well known for content collaboration with global thought leaders, authors, and creators. For more information, request you to visit www.innovationroots.com. Do's and don'ts: join the event 5 minutes before the start time. Use high quality speakers and headphones for better sound quality. Please keep your microphones muted and video disabled, as this may cause disturbance and bandwidth issue. Questions will be taken via chat box. Please feel free to enter in the chat box. At the end of the session, facilitator or moderator will help you read the questions out as per the time available. Please fill the feedback forms after the event to help us understand about the event management and the more sessions what you would like to hear about. We appreciate your cooperation. So with this, I would like to welcome Rashmi Tambe. Rashmi Tambe is a digital transformation leader with 20 plus years of industry experience. She is a multifaceted experienced, playing different role over the years. She has been a director consulting service at Hitachi Vantra, AI ML strategic principal, RPA practice lead, technical assistant to the CEOs, and presently she is a strategy lead for enterprise modernization, platform and cloud service at ThoughtWorks. She is an avid reader, TEDx speaker, and passionate about women in tech cause. Glad to have you, Rashmi. I would like to welcome you on behalf of the Agile Network India Committee. Over to you, Rashmi.
Thanks, Prashant. Thank you. Thanks to Agile India Network for giving this opportunity to talk about quantum computing. This is an area I'm really passionate about, have been studying for the last few years. And I really love to, in my spare time, I like to read about it. I like to connect with folks in the industry to understand what's happening in this domain. So it's fascinating to talk about this topic. I'll not spend too much time on this. Prashant has already given my introduction. After the talk, if you want to connect with me, you can do that on LinkedIn and Twitter, needless to say. So with that, without further ado, let me directly dive into the topic of quantum computing. I'm not sure how many in the audience would know about quantum computing or specifically about quantum supremacy. Google claimed that they achieved quantum supremacy in October 2019. And in fact, that was the time when I really got interested in quantum computing. Before that, as a topic of interest, I was studying quantum mechanics or quantum physics part of it. In October 2019, after this announcement came in, then I started understanding how quantum mechanics is applied in quantum computing. What this statement means is Google claimed that they did a calculation on a 54-qubit quantum computer. This computer or the processor is called Sycamore. And they claimed that the calculation took hardly 200 seconds, where the classical computer, or rather the most powerful supercomputer, would take 10,000 years to complete. This claim, after this was pretty controversial claim, IBM refuted it afterwards. 2 months after that, some institutes or some research groups in China claim that they have done even better. They have solved a calculation which a classical supercomputer would take 2.3 billion years. So these are tall, huge claims. But let me tell you that there's a lot that's happening in this field for last 20-25 years, and there are some exciting areas that we are looking at, and also some areas of concerns that we are looking at, and that's precisely why quantum computing is picking up. So let's first understand why it is needed, and is it a replacement for classical computer? It is not. We will continue to use our classical computers, which are based on standard logic of gates and bits. Okay, that will continue to happen. But there are certain problems that we are going to see in the coming future. The bullet that you see here, right, the third one. There are some very complex algorithms having polynomial complexity or NP hard non-deterministic polynomial complexity, which the classical computers are going to take years to solve, and we'll talk about some of those use cases further down in the presentation. One of the key things, why the why part is the first one, transistors. If you are aware of the Moore's law, Gordon Moore in 1965 predicted that the number of transistors and the computing power per square inch on the chip is going to double every 1.5 years. And his prophecy obviously has turned true. We have seen the gigantic amount of development that has happened over the past 50 years. So much so that today the smallest chip is around 5 nanometer. This was recently unveiled by Apple for one of their laptops, for which can do GPU processing, for which is required for deep neural network processing. Now, if you see 5 nanometers, it is so small that 5 nanometers is actually 16 oxygen atoms. That's how small the integrated circuit is. Beyond this, it's going to hit a wall. There's only so much further, so much miniaturization you can do, because beyond that, the electrons in the integrated circuit are going to, they are going to hit a wall. They are going to be so free flowing that the circuits are not going to work as expected. The differentiation between the circuit on and circuit off is going to go away, because it will be so miniature that the electrons can pass through on and off so easily. And that is where it's become the whole concept of parallel computing is also going to hit a wall, because there's only so much parallel you can do. There's only so much faster chip you can have. And some of the very, very complex problems that we are going to see further down, either it's very hard to solve using these parallel computers, or it's going to take a huge amount of computing power to solve these problems. And that's precisely why quantum computers present a very formidable alternative to solve these complex problems. So let's quickly understand what is quantum computing. So it's a new kind of computing which leverages quantum physics or quantum mechanics phenomenon, which is called a superposition and entanglement. I know there are many complex terms on this slide, and that's how complex quantum mechanics is. If we get time today, I know I can talk a little bit about what superposition is, but this is something that in the last 100 years, or a little more than 100 years, it has baffled the entire science community how the particles at subatomic level, particles like electrons and photons, how they behave at subatomic level. It even baffled greatest of the great scientists like Einstein. He never he could never make a peace with the concept of quantum mechanics, and till the end of his life he tried a lot to have a theory which can his theory was about theory of relativity, which works at a macro object level. That theory cannot explain how things work at a micro level, at a subatomic level. He tried a lot, it didn't work out. So it is still, even today, people cannot explain why things work the way they do. But the genius people like Richard Feynman, he was a famous physicist who in 1985 suggested that it's okay if we don't understand quantum mechanics. We cannot simulate these things at quantum level. But we cannot do that because our classical computers would never do that. So let's do something else. Let's try to harness how the particles behave differently. It's okay if you don't understand it, harness the concept of superposition to build a quantum computer and try to simulate the physics at a level, at that level, using the same level of complexity. And that's where the concept of quantum computing started. Obviously, it took many years from that concept to actually develop the quantum computer. Um, but that's what quantum computing is. It is, you still have chips, you still have gates, but the fundamental functioning is different. It is not on bits. It's based on something called as qubits or quantum bits, and we'll talk about how they are different than bits. Okay. So to understand a little bit about, what sort of problems of exponential that we're talking about that a quantum computer can solve, let's take a little bit of a different route here. Let's try to. I'm not sure if you are aware of this story of a emperor who was once presented a game of chessboard. He loved it so much that he asked the inventor to be, what do you want as a reward? The inventor said, nothing much, my king. I just want some rice grains, but they should follow a certain pattern. In the first place in the chessboard, let's place just one rice grain, and just you keep on doubling the rice grain on every position. The emperor thought, wow, this is like, you're not asking me too much, and he told his treasurer to reward this inventor. As it happens, if you do this, with every block or every square on the chessboard, by the time you reach the 64th block, you're looking at 18 quintillion grains of rice, which is impossible for any emperor, any treasurer to reward. And that's the complexity, or that's the exponential complexity of 2 raised to 64. Okay? That's the kind of problems we are talking about with quantum computing. When we talk about quantum bits, the most important thing that we need to remember is, a bit at any point in time presents either a value 0 or a value 1, whether the electricity has passed or not passed. Okay, based on that, it can represent only one value at a time. On the other hand, a quantum bit can represent all possible values. It could be 0, it could be 1, it could be a probability of 50%, 40%, 60%. And that's what makes it extremely powerful, because if you are taking a 2-bit computer, you can do all 4 calculations exactly at the same time, wherein for a classical computer you will need 4 iterations to do all 4 combinations: 1 0 0 0 0 1 1 1. Okay, you will need at least 4 passes to do all 4 and obviously you can parallel it, but you still need 4 types of cycles to do all 4 combinations. And that's exactly where quantum computer is extremely powerful. It does all these 4 combinations in just one cycle. Okay, and that's what it gives it the most exponential advantage. Just to put a anecdotal information here, if you have, let's say, a 230 qubit quantum computer, doesn't exist today. The largest one today was it was unveiled by IBM last year. It's a 143-bit quantum computer called Eagle. Okay, but let's assume that you do 230-bit qubit computer. The amount of information it can theoretically process would surpass the number of atoms in the observable universe. That's how big we are talking about here. It hasn't been achieved yet, and this is still at a theoretical level. There are a lot of issues in achieving this kind of supercomputing. The particles at that level don't make it easier for humans to do those calculations. There are many problems which people are trying to solve. But theoretically, if once we achieve a 230-bit qubit quantum computer, we can process the information which is more than the number of atoms in observable universe. And that's precisely why it makes it so interesting. So with that, where is the industry moving? Where is the quantum tech industry going? There are some amazing estimates. The one I'm showing here is by BCG. It says that in the next 15 to 30 years, which is by around 2035 to 2030, 2040, 42, This industry will reach to 440 to 850 billion. Okay, so closer to 1 trillion is where the industry will reach to. Okay. On the other hand, IBM calls this particular decade as a quantum decade because this in the last few years, especially after Google's announcement of quantum supremacy, there's kind of a race that's happening between all the tech giants. There is a lot of investment being done by IBM, a lot of investment being done by Microsoft via Azure Quantum. AWS is also making a lot of investment. Most of the governments are pumping in money into this. And the reason for that is there's a lot of pressure that is mounting to solve some of the exponential problems, the problems which are having a non-deterministic priority or problems of exponential order. There's a lot of pressure to solve some of these problems. These problems could be around discovery of some of the new materials. It could be around how the protein simulation happens for drug discovery. These are very, very hard problems to solve, and that's where the pressure is coming to solve some of these problems. The other reason why this is a quantum decade is because the technology now is at tipping point. As I was saying, there is a huge amount of investment that is coming in by the tech giants, by the universities. There are a lot of startups that are coming up in this space. And there's this whole ecosystem that is getting built around quantum computing. So the ecosystem is, there are startups, there are universities, there are industries, there are R&D departments of these industries, there are governments, the cloud providers, and hardware providers. So this whole ecosystem is coming together to solve some of these problems of scalability. And there's a lot of things that are happening in this space, and that's precisely why IBM is calling this particular decade as quantum decade. In fact, there is an announcement by IBM by 2023 they will build a quantum computer which will have 1000 qubits. So in the earlier slide we saw that even if you can build it at a 230 qubit level, you will surpass the number of atoms in universe. Now imagine what happens at 1000 qubit level, and that's how ambitious IBM is getting into this field. And that's precisely why they're calling this as a quantum decade. On the other hand, you will see a lot of startups coming in this space. There is suddenly in the last, as I was saying, in the last 5 years, there's a lot of new startups that are coming into this space, and they are also getting funded by private equities, getting funded by angel investors, getting funded by some of these universities or Microsoft, IBM, etc. In 2020, the total pure play quantum computing equity investment was around 700 million. Last year, in 2021, that investment became 1.7 billion, so almost more than a double. And we'll see this trend continuing. Most of the investment is happening right now at a hardware level because it is very, very complex to build the quantum hardware. So the image that you're seeing on this slide, this is the one of the latest quantum computers by IBM. The image that you saw on some of the earlier slides with all the golden wires, that was Google's Sycamore quantum processor. It is extremely hard to build these processors. It is extremely hard to keep these processors. They are kept at almost the temperature is colder than the coldest temperature in the universe. It is literally at few kelvins. It is the extremely cold temperature. You have to keep the qubits at that level in order to have any meaningful calculations and in order to derive some interference out of those quantum calculations. And that's why the hardware field is getting a lot of push, a lot of investments from the industry to be able to we are still not at a level where the quantum computers will be commoditized. We're still not at a level where you will see quantum computers at home, like your laptop as a quantum computer. That's too far away. It's not happening in near future because of the way the quantum computers work. They require a sub-freezing temperature, a very delicate handling, and that's precisely why most of the investment is going in quantum hardware. There's also a lot of investment happening in the system level, in the application level, in the cloud level as well. And that's exactly why the industry is booming. So one might ask, why, why so much hype? What sort of problems can these computers really solve? Is it just hype, or can it really solve any type of problems? Okay. So at a very high level, quantum technology as such is divided into three areas. Quantum computing is one area. The area that I'm talking about is just one area in quantum tech. Second one is quantum sensors, and the third one is quantum communication. I'll not talk much on sensors and communication because they themselves are very, very complex areas. Within computing, there are four types of problems that quantum computers can solve. The first and foremost is around simulation. Simulation is the ability to, for example, if you want to understand in let's say chemistry, how two types of molecules interact with each other, what sort of the atoms, electrons, the power between or the bond between these atoms, how does that react with each other? For doing that, the complexity of these algorithms is again exponential. The number of atoms, the number of electrons, the number of protons, the type of bond that you have, each of these parameters adds a complexity. Where it is needed is the creation of some synthetic materials, creation of or some advanced research in fluid dynamics. Why it is needed? For example, there are discussions about, for example, Elon Musk is saying that, okay, I plan to go to Mars by 2030. Some of these kind of explorations would require materials that can withstand the kind of radiations that one would face in the space, or the kind of heat that that the entire space travel would have to go through. All these complex scientific areas require invention of new type of material. So far, all these new types of materials are being tested in the lab, physically being tested in the lab, and that's why the research is very, very slow. Imagine a possibility of simulating all of that, how these atoms interact with each other. All those simulations can be done on quantum computer in a much, much faster manner than classical computer, and that's where the area is picking up a lot. Optimization, this is a problem where ability to find the best possible answers given variables. For example, what's the best possible or the shortest possible route to cover all the cities? Okay? These kind of problems are very, very significant in logistics, in financial optimization, in aerospace, etc. Third one is machine learning. Machine learning in itself is a very complex domain, and with the advent of deep learning, etc., there are many new things that are happening in machine learning, and it is beyond just doing pattern matching or image recognition. It is also at a level of understanding the human language, understanding the perception, understanding the tones or the sarcasm aspect in human language, understanding the facial expressions, etc. What's happening in machine learning is that with the quantum and the machine learning, there are some people are trying to solve some very, very complex problems in deep neural network. And finally, cryptography. I'll talk about cryptography in the next slide in detail, but these are at a very high level, four types of problems that a quantum computer can solve, which a classical computer would take years to break or would take years to solve. Okay? So here, let's take a look at look at the future. Let's say 15, 20 years that BCG is predicting where the industry will go. What sort of problems quantum computing can solve? We saw the four types of problems in the earlier slide. In the further slides, we will go deeper in those use cases, and we'll also see some areas where quantum computing will actually cause a problem than solving a problem, and that's where the biggest threat is coming up, and that's where most of the governments, the defense sector, or rather the defense departments of most of the governments are pumping in money, and that's the area of cybersecurity. Sundar Pichai, who's the CEO of the Google, he made a prediction, I think just a year back or 2 years back, that quantum computing will break the encryption, the RSA or public key cryptography encryption in the coming 5 to 10 years. Now imagine the havoc it will cause, because today the public key cryptography enables billions of internet users to securely access the websites, as well as engage in trillions of e-commerce transactions annually. The problem, if someone breaks any of these, the packets in transition or the data at rest, imagine the kind of havoc it will cause. Imagine the kind of havoc the military will face if the secured communication on the military channels is hacked by a hacker, and if the private key is guessed by a hacker. And that's where the most of the investment is coming, because of the fear of public key encryption is breaking. If you go a little bit deeper in technologies like RSA, they rely on a large integer or large number prime factorization. So imagine a 300 or a 500 digit number, which can be divided by exactly 2 prime factors. Okay? That's usually, that large number is the private key in the RSA algorithm. So there's a public key and there's a private key. Only the someone who has a private key can decrypt the message. Okay. If a hacker hacks the packet, because the hacker does not know the private key, it's very hard to break that private key. That's why the RSA encryption is very secure. Okay. It will take, again, it will take millions of years to break 300 or a 500 digit integer, to break it into 2 prime numbers and guess the private key out of it. Okay? And if you see the timeline here, on the timeline it says that the most aggressive estimate is that quantum computing will break a 2048 RSA algorithm by 2026. And the most conservative estimate says that it will break it in next 9 years, by 2031. That's precisely why NIST, which is the National Institute of Science and Technology in the US, the cybersecurity arm of it, has defined, it is in process of defining some standards around post-quantum cryptography. This is a field, it's called PQC. Uh, some companies like Microsoft is especially focusing on PQC as part of their quantum initiatives, in terms of what happens if the RSA cryptography breaks. What sort of cryptography algorithms are we looking at? And that's where most of the work is happening in the next few years around the post quantum cryptography work. There is a area, I was talking about an area of quantum communication. This area precisely does something similar, wherein if the messages are encrypted using photons, and not so the photons act as private keys. And there are some interesting physics principles that play in. If someone hacks that proton, it goes into something called as a collapsed way, which is then the hacker cannot, once the proton collapses, the hacker cannot break the message, okay, or cannot break the encryption. These are some very complex scientific areas, and that's where, as I was saying, many governments, the defense departments, and also the large corporations are specifically focusing around, when they are focusing on quantum computing, they're focusing on post-quantum cryptography in order to avoid the havoc. The next area is protein folding. This is a type of simulation use case that we were talking about earlier. And this has taken even more significance because of the COVID-19 pandemic. So the way usually the drug discovery or the vaccine discovery happens is proteins are nothing but these are sequences of amino acids. Okay? And these amino acids, the way they attach to each other, they form certain 3D structures. The way the 3D structures are formed, that's how that 3D structure determines their function. Okay? Every type of protein would have different chains of amino acids, and they would for different types of 3D structures. The viruses get attached to these 3D structures, and that's precisely what COVID-19 virus does. It gets to attach to a very specific amino acid in this 3D structure. And if you imagine a simple protein with let's say 100 amino acids, there are 10 raised to 47 potential combinations of how this protein will fold or how this protein will form a three-dimensional structure. Okay? That's where the drug discovery it's a very lengthy process, or a vaccine discovery is a very, very lengthy process, because they need to figure out very specific areas in a virus's protein structure to attach a vaccine molecule or to attach a drug molecule. Today, this is done in the laboratory setup by testing various permutation combination. Imagine all of this being done using a simulation. If you could simulate all these 10 raised to 47 potential combinations with a drug molecule combination, the drug discovery will be vastly expedited. And it also opens up a lot of doors to things like personalized medicine. For example, how today the vaccines or the drugs are manufactured at a generic human, as in it takes usually the clinical testing happens on a sample. The sample could be 1,000 people, but we are talking about 7 billion people on the earth. Every race, every the way people are conditioned in their own geographies, how they react to certain foods, etc., it differs. And that's where the personalized medicine can be very, very beneficial if you can simulate how the protein or how the drug will work on your body, instead of it getting tested on some 1,000 people, and then it's like a trial and error basis on your body. Okay. And then I was talking earlier, it also has a lot of use cases in fluid dynamics, in battery design, even in financial services, how derivatives or option pricing can happen. So all these areas is where the simulation, if you can simulate a scenario of possible data points, of possible combinations, any area where this kind of simulation is required, that's where quantum computing can help, because it can simulate all of it in parallel. It does not have to, when I say in parallel, all of it happens in just one go than in multiple parallel exponential ways. Okay. We are seeing some, there are some startups like Protein Cure, which are using quantum computers to predict how a protein will fold in every human's body. There are companies like Biogen, Merck. They are investing in quantum computing for early stages of drug discovery. Accenture has partnered with some of these companies to do, to expedite the clinical testing of drugs, etc. So there's a lot happening in this field using quantum computers. The next area is traveling salesman. This is a standard logistics problem. Most of the companies, whether it's an e-commerce company, logistic company, or even an aerospace company, you need a way to find what is the best possible order to visit various cities. This is again a polynomial a problem, because the number of the more data points you add, the more number of destinations you add, the problems start becoming more and more complex. And that's where again quantum computers can simulate all possible scenarios in one go. Companies like DHL is exploring ways for their global delivery routes. Volkswagen, along with the DWS system, they and few, I think they are doing a pilot with IBM as well for doing their logistical planning using quantum computers. KPMG did a pilot in financial portfolio management using quantum computers. Again, because the number of cities or number of data points that you keep adding into this, the paths, the shortest path or the best possible path to visit all these data points gets extremely complex. For you to find out which is the best path, you will have to traverse all paths to find out the best path. And that's where quantum computer, the exponential processing becomes very relevant. Last but not the least, quantum AI. This is a very early stage. There are some very basic prototypes that have happened. Startups like Xanadu, Zapata, they are doing some very early stage quantum AI related work. What quantum AI means is it's a hybrid model of using classical deep neural network along with quantum network to expedite the execution of a deep neural network algorithm. Okay. Again, because of the exponential nature of quantum plus the deep neural network put together, there are some extremely interesting problems which are getting solved by this, but this is very, very early stage. We will see more coming up in the next few years. Okay. And last but not the least, this is a beautiful diagram. This was created, this is created by McKinsey, where it shows the various industries on the left hand side. For example, you have energy, pharmaceuticals, financial services, telecommunication, travel and logistics. And you will see how is the impact of quantum computing that's going to happen in the next, for example, by the end of this decade, by 2030, and by mid of the next decade, by 2035. How is the impact? Is the impact going to be incremental, significant, or is it going to be destructive? And you'll see that the impact in energy, in chemicals, in pharma, it's going to be destructive by 2035. And you'll see the industry size here in trillions, how this industry is really going to grow in the next 15 to 20 years. And that's precisely why IBM is calling this as a quantum decade. Okay. So now let's shift gears a bit. We talked about what quantum computing is. It leverages superposition and entanglement. I won't be able to go into too much details of what it is, but I'll just show you one slide. Okay. If you know how classical physics works, we've learned this in our schools, right? If you throw a ball or if you hit a ball in snooker, there's only one well-defined trajectory that a ball will take from point A to point B. It will have a precise position, it will have a precise speed at all times. Okay. If you change the force of ball throwing, the trajectory might differ, but it's not possible for a ball to take all possible trajectories. Okay, for going from point A to point B. In quantum, this is exactly opposite happens. Okay, at a subatomic level, when an electron travels from point A to point B, it travels through all possible paths. Okay, and all possible paths at same time simultaneously, and that's what baffles scientists. How is it possible? Because at a macro level, you cannot have a ball take all possible paths from point A to point B. It has to take just one path. But at a subatomic level, that's exactly why it happens, and that is exactly what gets leveraged or harnessed in quantum computing. You do all possible parallel combinations. For example, if you take a traveling salesman problem that we talked about earlier, uh, if you have n cities and you want to find out the best possible path between these n cities, today the best possible, there are n factorial combinations that are available. All these n factorial combinations will be traversed by quantum computer in one go, not in n factorial ways, and that's what reduces the time it needs to do this kind of simulations or this kind of optimization problems. Okay. If you look at classical bits, at any point in time, a bit either would have a 0 or have a 1. It cannot have both the values. In quantum, it can have all possible values, and then there are probabilities. It could be 5%, 10%, 60%, 10, it could be anything at all time. And that's why it is extremely powerful, because you don't need for doing n order problem, you don't need n bits. You probably so basically with one bit you can do two combinations at the same time. With 2 bit, 4 combinations at the same time. With 3 bits, 8 combinations exactly at the same time. Here you will need for a 3-bit computer, you will need 8 cycles to execute 8 combinations. Here you will need just 1 cycle to execute 8 combinations, and that is what makes it very, very powerful. I may not have much time here, so I'll not cover the history. The history from how Richard Feynman started the concept of quantum computing to where we are today. The only thing that I would like to cover, which is very interesting, is Indian government is also not left behind in this, as all the governments are doing across the world. Indian government has also, they announced in 2020 budget that in the next course of next for 5 years, there will be an investment over 1 billion in quantum computing, and there are many good things happening in this. There's already a policy forum formed. There are a lot of experiments that are happening. So our government is also taking a very significant note of where this industry is going. Okay. A last section on this. You as a developer, how do you get access to this? And that's very important. So the slide explains the ecosystem. There are some companies like IBM, Google, Microsoft, Alibaba. They are full stack quantum computing companies. What they do is they provide the hardware, they provide the systems, they provide the software layer and the cloud services as well. There are some companies which only provide hardware and systems. There are some companies like QCweb, OneBit. They leverage these hardwares to develop some quantum applications on top of it. And then there are some very specific companies. The company I talked about earlier, Protein Cure, they are developing very niche protein folding problems for life sciences. There are many such companies who are doing that for a very niche industry vertical. Okay? In all, you'll see that the entire ecosystem is, you as an application developer. Then there are universities like, the Stanford, Columbia, there's Yale. All the top universities in the world are investing in some sort of quantum research. Some of these quantum research labs in these universities are eventually getting spinned off as certain startups. So there are many startups which have come from these universities. So you have a startup ecosystem, you have research labs from, for example, there's Accenture Research Lab, there is KPMG, there's Deloitte. All these research labs are also doing some work. There are organizations like all these pharma giants, financial services, they are doing a lot of work. And there are companies, doing the work at a smaller level. This is the entire ecosystem. And for you as a developer to access this, the good thing is that the cloud-based quantum computing is available on top 4 cloud providers: IBM, Google, AWS, Azure. Between these top 4, the best one today, best one in terms of the developer resources, free access, etc., is IBM, because it also provides a quantum developer certification. Azure is also making a lot of progress. They provide the best credits. There are almost 500 Azure quantum credits you get if you sign up for Azure services. AWS also provides it. Google provides it, but you will have to apply why you need it, etc. It is still a little bit closed system, but you can get access to Google's quantum computer as well. Many of these cloud providers, what they are doing is, in IBM and Google, they provide access to their own quantum computers, as well as partners. For example, they have partnered with certain startups, and they provide access to partners' quantum computers. They also provide access to something called as quantum simulators. These are not exactly quantum systems, but they simulate the quantum behavior. AWS and Azure still haven't developed their own software, own hardware. So their entire ecosystem is completely based on partners. But nevertheless, as a developer, if you want to do certain algorithms, it is the democratization of quantum computing is just happening. So you will be able to access some of these services. Okay. So with that, I think I'll come to the very last slide. I'm not sure how many of you know this particular image. This image is it was taken by a spacecraft called Voyager 1 in 1990 from 6 billion kilometers distance from Earth. The ones that you're seeing, these are so the spacecraft was beyond Saturn, and it took a last photo of Earth overlooking Earth beyond Saturn. So what you're seeing here is these are rings of Saturn, and this dot that you see is this is the dot where we live. Okay. If you look at the scheme in the universal scheme, we are this tiny pale blue dot. Okay, we are this small. But what fascinates me about this whole thing is, this one insignificant dot is creating a computing power which can simulate or which can process the amount of information which can encompass all the atoms in the universe. And that's precisely where quantum computer becomes extremely, extremely powerful. Okay? This one insignificant dot becomes extremely significant in the whole scheme of things. Okay? So with that, I'll take a stop in case of any questions.
Thank you, Rashmi. This is really something thrilling and exciting to see something so new. uh, so we have a couple of questions. Mr. Raghupati asks, does supercomputer runs on quantum computing? Anything you would like to?
No, none of the supercomputers today run on quantum computers. They are all are standard classical computers. Obviously, they are very, very fast. Uh, as I was saying, the fastest, one of the fastest that Apple unveiled is the 5 nanometer M1 laptop chip, which is something that they unveiled for GPU processing. Intel has 14 nanometers. So all these are classical integrated circuit based classical computers. None of them are using quantum computers. It is, the classical computers, it will never use quantum computer in its, as in, it will always be a hybrid model. There will be classical computers, there will be quantum computers, and they will always work together. We are not seeing a replacement of classical computer. That should not happen. That will not happen. They will continue to work, but they can work in tandem with quantum.
That's interesting. And following with that question is, does the system require high energy? In that case, is it environment friendly? Is there any thoughts going on that part? Is it like?
Yes, yes. That's a good question, actually. See, any system that requires a huge amount of computation is never environment friendly. Okay, take an example of cryptocurrencies or bitcoins. Okay, the amount of energy it requires you to mine a bitcoin or to compute the hash with which you can you compute the hash, and then you register your record in that entire chain of blockchain, right? That in itself is not an energy efficient computation. It is always detrimental on the environment. And that's precisely why, if you look at classical computers, the amount of time and computation they will require to break some of these simulation problems, optimization problems, that is huge. When we reach a level where quantum can solve these problems of protein folding or simulation, they will use very, very less energy, because they will not, they don't have to do parallel processing for breaking protein simulation. Okay, they will be, as I was explaining earlier as well, it is very hard for us to imagine how it will happen, but imagine that all possible paths of computing happen in just one go. And it's not parallel computing, because in parallel computing, all possible paths of computation happen parallelly, which means that if there are n paths, all n paths are happening. Energy is getting consumed for all n paths. In quantum computer, the energy gets consumed for just one path, because all n paths are happening in one path. Having said that, the way quantum computers work, I was explaining earlier as well, that the computers have to be kept at sub-zero temperature, extremely cold temperature. That entire infrastructure itself takes energy. That's a huge, Google unveiled a campus, quantum AI campus in Santa Barbara. It's a massive facility. And that's precisely why not everyone can build quantum computers. It's a huge energy requirement and very complex mechanical ways to keep quantum computers running. So short answer is that any type of computer, even the quantum computation, will not take energy. The whole functioning or the logistics of running quantum computer, that will be very energy greedy.
True. And I can see Amar Also accepting that quantum physics and computing is super complex.
Yes.
So obviously, uh, uh,
Uh, I did
yeah.
not I didn't cover on the superposition aspects or the exact basics of quantum physics. If people are interested, read about something called as double slit experiment. Okay, this is one
Mhm.
of the mothership of experiments which explains how weird quantum mechanics is. And the concept I was explaining, that the qubit can be both both 1 0 or anything in between, uh, that is based on the concept of superposition, which is explained by this experiment called double slit experiment. You can also read a lot about things like multiverse. So these are all, entanglement. These are all extremely complex physics phenomena, but and that's precisely why it's very hard to get people who can develop quantum computers at that level, because you don't just need computing, you also need understanding of physics. While on the applied quantum side, you may be able to do it with usual set of developers, because there you just need to understand computation.
Exactly. Actually, I was about to come there. In fact, like you touched about that, where people can start, but still, uh, the curiosity is driving me. Like to ask you, what is the basic qualification required if somebody wants to look into this particular part of as a career?
Correct.
And
So
is there anything related in the university, something, or it is completely new?
On the training side, there are many courses that have come up on Udemy, which can help you understand. For any developer to start into this, there are two, three basic things that are needed. One is you need to understand the linear algebra. Okay, you need to have the background in, at least in Python, because most of these quantum SDKs. So there's a quantum SDK by IBM called Qiskit. Google also has a quantum, I think they have TensorFlow Quantum. Okay, all these are Python-based SDKs. So you need to have the basic knowledge of Python. You need to understand linear algebra. And the good thing is that there are good courses on Udemy. At least that some of the courses that I have done are on Udemy, which explain you the basics of quantum physics, explain you the basics of linear algebra that is required. So you, just like a machine learning developer, you need some amount of background in mathematics and Python for this. Beyond this, if someone is interested, they can really go into the details of physics. Some basic understanding of physics is required, but not at a level where you are developing algorithms. As long as you know how these qubits work, that's fine.
Thanks a lot, Rashmi. I think this is something really new for most of them. And I would like to thank you on behalf of the uh, community, as well as really it was something refreshing, and we can see which way things are going now. So thank you very much for sparing some time and sharing this particular insightful thoughts about quantum computing.